Okay, so this is now the second session. We're doing this monthly, so just a little bit of a refresher. I'm going to go through that today, but next time we're going to be talking about, Roberto's going to lead something on resting state. Today I'm talking about sort of the second, last time I talked about sort of single subject level analysis and processing. Today I'm going to talk, just to walk through the process of group level analysis. And then in June, Michelle's going to talk about connectivity, right? So this is still the plan. Now I'll try to send a reminder email about it. What do I got to do? Click it. There we go. Oh, it's that. Okay. Okay. So this main thing I'm going to talk about today is a study with the FACES task, where we're looking at two groups: people who had epilepsy, people who don't have epilepsy, and this task where they have different faces. So there are different emotions. So they have fear emotions and happy, sad, angry, and no emotion, and then they have to the whole series of trials. So basically, a motion recognition task. What emotion was this? So this is basically what they see over the course of, I think, 2 runs. And last time we talked about the pre-processing. So you go through, basically what you do is just single subject analysis, and then you carry that through the second level. And what we did is the brain basically gets divided into these different voxels. So it looks kind of like this. And there's a whole series of processing steps that we do to make sure that everybody's exactly the same orientation, that the data is smooth, that motion is removed. And then this is the actual, this is a shot from AFNI. This is the actual bold signal that's going up and down across time. And what you end up doing is adding some regressors into that for when each of the different types of stimuli that you're interested in were presented. So like a first fear face, the first angry face, the first sad face, the second fear face, and there's a timestamp associated with each one of those. And then from that you create a regressor that what we expect the bold signal would look like if it was responding to this stimulus at this time. Sort of multiply this signal by this, and the extent to which this looks like this, you get a probability that it's really responding to that stimulus. It seems to be acting as if it responded to that stimulus. So that's basically what I went through last time. Whoops. And you end up with something that looks kind of like this at a single subject. So this is the sort of raw structural MRI data, the raw functional data. It's a whole series of them. And you end up with something that looks like this, which is really just a probability map of laid on top of this individual subject's structural image. The color scale is the probability that different things, and I think this is probably everything that was in the task. So the probability that these different areas were responding to things we did during the task on this subject. And we tend to, when we do it, just kind of a sanity check to make sure that we're coding things correctly and that we're grabbing something. We usually have some big thing where we look at how much of the total variance is explained. And a task like this, where we have a lot of visual stimuli, expect to see some really strong activation in visual system. So usually when we go through a single subject, we check just to look at it, say, okay, it looks like it does look like it's supposed to look, before we do a whole lot else. Okay, right. So last time, one of the things that Sandra asked me was, after I talked, was how come there's activation outside the brain, which I think a good question, and probably where's Harry? I wonder if he's supposed to be coming here. But it's also an opportunity to really think about what it is that this represents. So what that color scheme is not activation, okay? It's a probability map, and it's not just looking at the brain. It's looking at everything that is within the MRI space that's collecting. So you get this all the time. You get these sort of what they look like spurious, but they really are. These are
areas that were in the overall space that looked like they significantly were related to, the fluctuations were related to the stimuli that we presented, the task. So you do see that, but it's not. A lot of times people talk about this as if it's activation. It really isn't activation. It's a probability map. Okay, so then after you take all the individual subjects, what you do is you put it into a group level analysis. And this is sort of standard, what most people do with group level analysis. For this thing, we did an analysis of variance using this thing called 3D MVM. There are several different functions within AFNI that you can use. This is probably the most flexible one to do an analysis of variance. So for this particular case, we have our two groups. We have our epilepsy group, our control group. Because we have a very large age range, we have to look at age, and age is actually one of the biggest factors in this. So kids range from 8 to 18, so that was actually entered as a separate column in the regressor, basically. We have so those are both between subject differences, and then within subject we have the emotion, so whether they saw a sad face, an angry face, a happy face, and you have all these different interactions. So basically you do that, and let's see. And then what you get, and I'm actually going to open up AFNI here. You end up getting, this won't show up on the screen, will it?
It will.
It will?
Yeah.
Okay. Hey, Harry. Sorry. We switched rooms.
Escape will do it. Yep, we're still good.
That's good. Okay. So this is now opening up our server into the Baker cluster. And this is the output from one of the analyses we did. You open up AFNI and you get something that looks like this. It's a whole bunch of different windows. So the first thing that you get, this is the sort of template brain. This is a single subject, but it's a single because so you can see all the little gyrations, but it's actually been put into a standard space. So there is, if you see up here, this X, Y, Z. So this is all individual subjects were put in the same warp so that they fit exactly this person's brain. And if you go through here, you can see the X, Y, Z coordinates change. The X is going left to right, the Y is going back to front, the Z is going up to down. So each one of these coordinates represents a specific place in the brain. And then what you do at the analysis level, so you get all of these 3D MVMs. These are all different ANOVAs that were run. So I'm going to put this one on. And this is now laid on top of the structural image. This is the probability map, okay? And you can see that it looks really noisy, but one of the things about AFNI is that they have this a scrolling probability bar. So if you push this up, you're increasing the either F or T value, you're decreasing the P value, and you can see that a lot of the noise goes away, and you get this sort of, these areas have a really, really high probability of being associated across the whole group. And you can scroll around here, and you can see these are the different images, different sort of orientations. And then what you get up here is these are the different, so that's the whole, it's the intercept. If you go here, you have, these are the different conditions that went into the analysis. So you have a group, age, group by age, emotion, group by emotion, age by emotion, group by age by emotion. And so each one of these will result in a different overlay. And so what this basically is saying is that these are the areas, oops, I need to change this too. I'm going to bring this down. So obviously, p-value is a little high for that. So this is now a p of 0.0078. So these are the areas that show significant group differences across the whole task at with the threshold set to 7.6 F and the P of 0.007. Okay. One of the things that you still see stuff outside the brain. A lot of times people will mask that out because they don't really care about that. But things still show up. And one of the big issues with imaging is you're always dealing with type 1 and type 2 errors, right? You have so many voxels that go into every analysis that there's going to be some, and it's probability, right? So there's going to be some that are just by chance probability are going to be showing up. If you correct to like the sort of Bonferroni correction kind of thing, where you look at correct for every single voxel that's in the brain, you're going to have effects that are so huge that you're never going to see anything. So this is always a struggle for people doing imaging. The main way that there are two ways that people deal with it. One is that there are all these sort of mathematics of looking at not just the significance of one voxel, but also the probability that two voxels next to each other. So it's a spatial correction. And with the bold signal with fMRI, you tend to get sort of a spatial distribution of it. So a lot of times what people will do is they will use a correction factor. They'll set the probability of being 0.005 and having 4, 5, 6, 10 voxels next to each other is sort of a sufficient correction for having for those spurious results. That's always exactly how you set that is always an issue. Every paper you write, you have to talk about that. So what you'll go up here is, let's see, this. So let me bring this down a little bit so we can see. So as I bring this down, more stuff is coming up. And maybe I'll do age. No, age. Come on, there we go. Yeah, both of these. So if you go to this thing in AFNI called clusterize, this sort of sets how big your spatial correction needs to be. So this is now set to 20. So if I go like this, a lot of the smaller ones will disappear. Let me clusterize even more. So let's set this to. Oh, I'm going the wrong way. How did that happen? Let me set this to 50. Apply. So more and more of these things start going away. Set it to 100. No, actually this is good. And then you go like this. And then you can bring this p-value up. It's really kind of slow. But so anyway, that's what you get. And it's walking through basically an ANOVA. You can do t-tests. For this is an ANOVA. And then you get this F value, right? That says, okay, this area in this brain, and let me go back to to my PowerPoint here. Just go to how about that? Oh, if I do this, will I overwrite it? There we go. Okay. So this was one example of a model. So you get something like this. After all your corrections, you get this area here, which is a group difference. So that means that area in the brain is showing the probability is that this area is different between the two groups across the whole task. And then you get something like a group by age difference. So that area there shows a different interaction. So across age, that area is different between the two groups. So there's sort of a different trajectory. And then you get like a three-way interaction where you get these areas are ones where the group differed by age as a function of emotion. So it's just like other ANOVAs. When you get to these high-level interactions, it gets to be a little bit hard to interpret them. But that's what the sort of ANOVA map is. So what you really need to do, first of all, one of the things you'll find, almost all imaging studies, you're going to have a lot of stuff that's there, hopefully. So you're going to have to kind of go through and figure out some of it you're really going to have to drill into, and some of it is probably not something you're going to drill into, because paper can't handle 50 different activations, especially with something like this where you have lots of different interactions, main effects. So you kind of have to make some decisions about what's important. So usually the first thing to do is kind of just spend a day walking through all of the different images and seeing what the different activation patterns are, sort of super threshold. And the things that are really big, you got to look at. You got to figure out what is driving that. And then a lot of what is important, what tells you that things that you really need to drill into a little bit further is what's important based on the literature. So if you're doing something on, say, depression, a group with depression, and you're finding a difference in an area that is related to, like, the amygdala or the ventral striatum, especially in the context of your task, that's probably pretty important for the phenomenon you're studying. And part of that is just the knowledge that you have. I mean, so you over time, this is really an important finding, and these things are not important. So then what you have to do is, once you find those things, you make a table of everything. So usually what you do is you make a table of, sort of a comprehensive table, everything you found, and then after that you do like graphs and plotting of things that you think are important. So the imaging tables tend to look something like this. So let me sort of walk through this. You have like your ANOVA factor, so your group factor, your age factor, your emotion group by age, group by emotion, age by the three-way interaction. And then next to that, in each one of these, you have where those sort of at a global level, where those things are. So, and this is not necessarily, people vary a little bit in how they report this. People may just say frontal cortex. People may say temporal parietal junction. People may say, and it depends a little bit on kind of what your task is about and what audience you're talking to. So a lot of times for this area, there is something that looks like it's sort of PSCS, which is an area a lot of people talk about in social cognitive processing. So I would put PSCS as an important area. And then you have the side, whether it's right or left. And then you have sort of somewhere you have something that indicates the values, your threshold level. So the cluster that you found, usually it's the peak voxel within your cluster, what the F value and the P value is of that specific area. And then most people have something that indicates how big these things were. So, and it's sometimes it's the number of voxels, sometimes it's the microliter size, actual size. And one of the things that you run into sometimes when you do this is you get these clusters, because it's such a strong effect that things blend together, that you'll have a cluster that's got, it goes from the temporal lobe and it goes all the way up and covers the cingulate. So you kind of have to look out for that, because really that's not going to be a single functional thing. And you probably would have to go in and cut that up somehow. And that happened with this when I was looking through this data set. There's one area that's like huge, and it's actually like half the brain. So this is making me crazy. So the next thing is actually putting it into the standard space. So for each of these activations, there is this, it's in this normalized spatial grid framework. So there's an X, Y, Z coordinate for each voxel you have. And that's something that people always report. What is the X, Y, Z coordinate of the statistical effect that you have? And the other thing is they often refer to something called a Brodmann area. And a Brodmann area is this guy, he was Canadian, I think, wasn't he? What are you doing?
Down now works.
So down works and back and forth don't?
Down works when you're not presenting, and then it's left and right. Yeah.
Okay. So the Brodmann area looks something like this, and this dates back to like early 1900s, 1909, I think. This guy went through and sort of microscopically defined all of these different regions in the brain based both on sort of cell types and their connections. And people still use this system to say which Brodmann area it is. They've done something like this also in monkeys, so you can kind of talk about, and there's some homology between them. So you can see that some areas are still pretty big, but you got some areas that are smaller. Now this is only for the cortex. You don't, areas like the amygdala, striatum, thalamus, those are not in there. But any neocortical area, we'll talk about what Brodmann area it's in. So that is also something that, so in your big table, you say what Brodmann area the activation came from. Okay, so then after you make your table with everything, then you go in and you say, okay, now I'm gonna really highlight the most important things that I found in this big mass of data. And I got this from Michelle. So in this task, we were looking at emotion differences between the groups. We found this one area in the sort of hippocampus amygdala junction that was different. So that's obviously an important thing for what we know about sort of emotion processing, and also because this epilepsy group often has problems with the hippocampus and medial temporal lobe. So this is something I think is important. And then you can get this little area here. So here's the XYZ coordinate. K is another way people refer to how big the cluster is. So K of 4 is pretty darn small, but it's a pretty cool area. So then what you do is you want to understand what is that group. This is a group by emotion interaction. So what does that mean? So what you do then is you go in and you create a mask of that area. And what that means is on your group level map, you take every voxel that is within that cluster and multiply it by 1. Everything else in the whole brain you multiply by 0. So then you have this little area that is your activation that you care about. Then what you do is you go back to each individual subject and you pull out, usually people will pull out an average of activation across those areas with all the different conditions. So then you get this much simpler data set to work with, and you pull it out, and basically in like any other data, like SPSS or something, you put it in and you say, okay, well, how did this react for the yellow one are the controls, the red ones are the people with epilepsy. How does this look across these different conditions? So this is what the activation looked like when they saw the neutral. This is what it looked like when they saw the anger. This is what it looked like when they saw the fear, the sadness, and the happiness. So what you can tell from this, originally you just see there's this blob in the hippocampus. But what's driving this is that basically there's a difference in the epilepsy group, and the epilepsy group are showing actually a reduction in activation in this area when they're seeing the fear and the angry faces. The other thing that is that's important to do with a lot of MRI studies is to look at how it relates to if we have them do some task inside the scanner. So usually you have them, if for no other reason than just to make sure they're awake and they're doing something. Sometimes we just have them push a button every time push a button every time I hear a bell. We don't care about it, what they're doing, but just to make sure that they're paying attention and that we know they're paying attention. For this one, we had that memory or the recognition task. So we asked them what emotion was this. So this is then just sort of a traditional looking at things like you would look at any other sort of NIH toolbox kind of task. So this is their performance. So how accurate were they when they saw a neutral face? And this is from 0 to 1, 1 being 100% accurate, and 0 being completely inaccurate. So probability, if it's just purely chance, it would be about 0.2 to the 5. Is that right? So inside the scanner, what we see here is that the controls are pretty, 75, 80% across all emotions that are identifying them correctly. The epilepsy ones are having particular problems with anger, fear, and sadness. You know, a couple of the same ones that they're showing a hypoactivation in their area, in this area up here. So it's kind of important when you get sort of in drilling into the data to look at both, unpack these big effects and to try to understand them. And if you have anything in your task that you can look at to help interpret or sort of pull out what it is you're looking at, it's important to do. And the way to do that really is to you go from, sort of pivot from the fMRI, this big, voxel-wise analysis to like a traditional SPSS type of thing. Okay, so the other thing, I'm doing okay on time, right?
Yeah. Mm-hmm.
Okay. So the other thing that people will do to try to relate imaging findings inside the scanner to other findings that were done outside the scanner, is there will, a lot of times, especially people do the kind of work we do, there are all kinds of questionnaires or clinical assessments that are done outside and that are available, right? So one of the things you really want to know is, okay, if these guys have a problem with their amygdala hippocampal response, does it relate to anything? So you might want to say, well, these guys really have a hard time reacting behaviorally in the classroom. So you'll get a CBCL score, or you have some other questionnaire responses that they whatever, anything you could think of that people usually do here. So what you want to do to really sort of make your imaging data more interesting and relevant is to relate those two things together. And there are two ways to do that sort of thing. One of them is kind of like what we did here, where you'll take your areas that you think are significant. So this might in particular be something that you want to keep looking at, right? And you do the same sort of thing that you did with their behavior inside the scanner, but you're actually now look at it in relation to the CBCL score or your impulsivity measurement, right? And that's probably the most common way of doing it. The other thing you can do is take some measure that you have that you think is particularly important. Let's say it's a depression measure. And if you have a single measure or a couple of measures, you can take that and put it into the original analysis, and then you can get an output of sort of voxel-wise that these are the things that significantly scaled with their reports of the depression rating scale, Hamilton depression or something like that. That's less common because it gets awfully cumbersome awfully quickly. So it's probably only if you have something really, really important that I would do that. But this is kind of the standard way. And I'm just going to walk you guys through. I don't really have data, but this is something that we've been thinking about doing right now. So I'm going to sort of take you through what our plans are for this. In looking at a new study, this is a different study in which we looked at, where am I at here? We're looking at testosterone, the effects of testosterone and impulsivity. So I thought it was a really good example of how we might do this. So we're doing this study where we're looking at kids who have adolescents who are gender dysphoric, transgender, and are getting treated for that, but with exogenous hormones. So in this particular group, we're looking at kids who are getting testosterone, and they're getting testosterone administrations at different doses. And there's a big interest in all the changes that happen emotionally, cognitively across adolescence. How much of this is driven by sort of normal just brain growth and expansion? How much of it can be attributable to specific hormones at puberty? Because puberty hormones have a lot of effect on the brain. So that's kind of the idea with this. And impulsivity, risk-taking, is one of the things that people is changes across adolescence. So we did a couple of things here. We have three measures. One is inside the scanner. We are having people do this kind of standard, called an established task. It's a gambling task. And then we also have them outside the scanner do a couple of things. One is this thing called a delay discounting task, and I'll explain that in a second. And then the third is this sort of a standard impulsivity questionnaire. How wiggly are you when you go to a movie? How much can you inhibit? Or it might even be, I don't know if it's a parent questionnaire, whatever. It doesn't really matter. It's some standard measure of impulsivity trait. So the gambling task is called the jackpot task. And so what we do inside the scanner is they have a whole series of trials where they have they see this sort of one-armed bandit. And then they can either decide, so they see this, and then they say, do I want to play on this or pass on this? And you can have this would be a low-risk condition, because what they're doing is they're seeing how they're trying to get 3 in a row. They have 2, they get 3. Then they have a high-risk condition where they have 1, and they have to get 3 to win. The winning is, it's points, but we sort of tie it to money vaguely. And I think in losing, if they don't win, they also they lose points. I think. Is that right? Yeah. So it's kind of a risk-based condition. So if they pass, they just move on to the next trial. If they play, then this thing they're spinning, and they can either win and they get this little ding and they get all this money, or you lose. And I think there's a sound or something like that.
Yeah.
Right? Anyway, you got to win or lose. So this is what we're doing inside the scanner. And there are 3 events that we're modeling. One is when they're making their decision. So do I jump off the cliff or not? Do I play this game or not? And the second is after they've made their decision, there's now this period of time when what's going to happen, the anticipation period, and then the outcome of whether they win or they lose. So this happens again and again and again and again and again, and we get sort of their brain response to this. And the 2 things that we did outside the scanner, one is the delay discount. So delay discount this is a pretty standard task. People have done it lots and lots of times. There's sort of norms of how adolescents respond to this. I think this is one of the normative studies. You ask kids a whole series of questions. Would you rather have $900 today or $1,000 tomorrow? I'll take $1,000 tomorrow. I'd rather have $900 today or $1,000 next week. I'll take $1,000 next week. $900 now or $1,000 next year. I'll take $900 right now. And you go through that whole series of questions. You kind of titrate where their level of how much they're willing to wait to get their reward. And this changes across adolescence. So older kids are more willing to wait for 6 months or a year to get. So that's basically you get this a whole bunch of mathematics that look like this. You get different numbers for their K value and their indifference point. So we did that. And the question is, does testosterone affect this? And then the second thing is this Barrett impulsivity score. And this is just this traditional whole bunch of questions. I do things without thinking. I squirm at plays, movies, et cetera, so you get a number from this. Okay, so our plan is to, there we go. First, we want to model the imaging, what happens inside the scanner during all these different conditions. So we're going to basically look at the effects of testosterone on each of these 3 things. And I can show you, I think, what the data is looking like at one person's level. I have to get out of here. Okay, so let's see, where am I? So jackpot. think I'm just going to go into subjects. We've only done this on like 10 subjects so far. So these are each individual subject, just so to orient to what this is. Each individual subject, we've modeled the testosterone. Effects on here, so I'm going to go into, I probably should have figured out which one I was going to go into. I'm going to go to 5. Results. Okay. So load up AFNI. There's Bob Cox. There's the guy who wrote 3D MBM. Okay, then I put stats. And then let me go decision. So each one of these is a different condition that we modeled at the individual subject level. So this is what you get. You can see here's the probability map. Probability is set to basically 0. So it's everything's active, right? Everything is probable. Let's see. So we should, I hope this is a good one. Oh, that's not bad. So what we see in general, what we have been seeing is this really strong activation in, this is not a great example, but in the sort of ventral striatum at these different conditions. So when they're making their decision, when they win a reward, and that's been a pretty consistent, almost every subject is showing a pattern of activation in response to that condition, right? Which is exactly what you expect. I mean, people have shown that lots of times. This is sort of the reward area, responds to winning something. It also is when you are making a decision about whether or not you want to do something. It's also an area of something that's rewarding. It's an area that tends to be active. So what we're going to do is go through all of this and get the variability of each subject in response to those 3 conditions that we looked at. So then each subject will have 3 numbers from the MRI. Okay? And we'll take those numbers. And so first of all, we expect to see that the testosterone is going to modulate those numbers. Predicting they're actually going to increase the degree to which your striatum is active when you're making those choices and when you win something. And that's based on past studies that people have seen that testosterone relates to that. Then the question is, because sort of at the level, at the conceptual level, these things are all related. I do want to close this, right? Yeah, I'm not going back to this. Come on.
It's just the mouse losing.
There we go. That's it. Okay.
Yeah, if you just click on that.
That's good. That's all.
Yeah.
So
Just make sure.
what we're going to do is we're going to take those 3 measures that we got from imaging and then put them into our analysis of the delayed discounting and the Barad impulsivity score. And what that will hopefully do is we're then going from the level of having some sort of mechanism that we are seeing is modulated by the testosterone, and that then also relates, at least to some degree, in these other measures of behavior that we're getting outside the scanner. We haven't quite done it yet, but hopefully in 6 months or so we'll have some data on that. So that's it. How's my time here?
Plenty of time. 38.
Okay. So those are kind of ways that people. The whole point of doing this is to show ways that you can think about how to take imaging data and incorporate it with, first of all, understanding it at the group level, what you get out of imaging data, and then secondly, kind of what you can do with imaging data. So all this is kind of standard what people do with functional imaging. It's really important to get, so you can get, with functional imaging, you can get, a task, like the gambling jackpot task, will take 20 minutes, 30 minutes inside the scanner. And you can maybe do 2, maybe 3 tasks at most. So you do have to think a lot about what task you want to use inside the scanner and what you're going to be able to probe and get out of it in relation to your wider study. Yeah.
Just more conceptual question related to that. So in the behavioral task in the scanner, is there like a situation where you want to make sure the performance between groups is comparable, so you can make sense of the brain data, or you can always argue the brain data kind of add extra layer to more sensitive to explain?
That's a really big issue.
So the question is,
Well, a classic example of this was people who did autistic kids, and they had them do some sort of a social rating, and they found that there's low levels of the amygdala in people with autism. But they weren't doing the task in the same way. They weren't looking at the faces. They weren't looking at the eyes. And when they made people look at the eyes, they actually had sort of normal levels of amygdala. Yeah, and there are lots of situations where if somebody, they're just not able in some memory task and they can't remember it. So how do you deal with that? So on the one hand, you want to have a task that does tap into a meaningful difference between groups, but you also have to be really careful that if you have some group difference, it might all be sort of an artifact of the fact that they're not doing the task the same way. So that's one of those things where you can go, it depends a little bit on what exactly the question is, but it's something you do need to be careful about. What else? That's all I had for today.
So I have one.
Yeah.
So when you make those tables in the beginning, so
Yeah.
you manually input those and then
Yes.
so the question was whether
Yeah.
inputting, whether
when
we
you
generated
generate all
the
these
tables. Yeah.
How do you do it?
So I don't think that's changed. It's still manual, but what you can do here, I'll just close out AFNI. There's a function in AFNI where you can push a thing and it will give you it'll spit out table. Most of that information is in the table. What you have to do then a lot of times is go from there and take it, and you have to do some interpretation of it. Like it's sometimes the coordinate systems are different and the voxel size or something is different, but it's like 80% or 90% can be generated with AFNI, and the SPM is another one, and that will spit out a table for you. So for the most part, it's done already. Yeah.
I usually do manually from that table because it lets me go through each of the clusters and think about it also.
Yeah.
So it forces me to look at all of them instead of just saying, oh, it's in Acunius or whatever. Sometimes it's on the edge of the brain and it's like, well, do I really count this as being? So it'll come up at a cluster. Sometimes it's even outside of the brain. I don't really need to transfer because they're outside of the brain into the table. So it kind of forces me to go through and decide which ones I want to then probe next. So it's like a necessary.
Yeah. Another key aspect too with this is where we're labeling things like the Brodmann areas and the regions. Those are from atlases that have coordinate systems, but it doesn't mean that exactly that was the area for each person. It's our best overall guess because it's not a one-to-one thing. So that's kind of why I think a little bit more human intervention is helpful for deciding where things are. But the coordinate systems are where we found those things. It's just what those coordinates exactly mean. It's kind of an interpretation part.
Yeah, when you do, there is just inherent variability in person to person on some areas of activation. Like, that will be language tends to be in this, where Broca's area tends to be in this area, but you can't say precisely where it is. But then you also lose some of that when you go from when you put everybody into this sort of normal space, when you're stretching and pulling and crunching. So whenever you get your activation, it's kind of, this is the neighborhood where you're seeing it. You can't be overly rigorous on saying this is exactly what we see in all subjects. So all of this is one of the reasons I think it's hard to go from like this approach, a group level approach, to like the clinical approach, because you just can't do. It's a very different approach looking at a single subject versus a group of subjects and probability. Another thing that people do sometimes related to this is if they have a specific thing they are really interested in, like the place I see people do this a lot is the face. There's a face area, so you will do a localizer. So for every person, what you'll do is you'll start with saying a whole bunch of faces, a whole bunch of houses, and you find an area that's in this general region where each person is the peak activation, and this is their fusiform face area. Then what you do is you take that data out and you pull that into all the different analyses, and you don't really worry about doing these group level things. And if you have a question that's really tight like that, that's probably the best way to do it. Auditory stimulation or language. People could do something with language. Find the language area in each person, and then be able to take that and use that in like an SPSS kind of an approach. Okay. Anything else? Is this helpful? Okay. So next time we're going to talk about is resting state, which is looking at the same sort of bold patterns going up and down, but it's completely unconstrained by stimuli or tasks. It's just intercorrelations of the brain, and it's kind of slow fluctuating. And there's a lot of interest in this. There's also a lot of controversy about it, but it's certainly something, there's a huge amount of data on it. People are spending lots of time doing heavy analytics on that data. And we know a little bit about it. I wouldn't say we're experts, but we've developed some ways of dealing with that data. And then after that, one of the things that another thing you do in this sort of group level analysis is functional connectivity. So that is actually looking at sort of trying to get at network. So if you had something like this, looking at an area that's different in these groups, does it connect differently with different areas of the brain? So maybe what's really happening is there's a circuit that involves some area in your frontal cortex, and your amygdala is related broadly. That whole network is down. So looking at how different things relate to that. And I think that's most. We're going to try to get into machine learning. This is also something we haven't done a whole lot. We're starting to learn about it. But again, that's something that's a big thing, up and coming thing now. And instead of taking the traditional ANOVA type approach, you're saying, okay, computer, tell me what is different about this data. And then that's all the functional stuff. After that, we're going to get into more sort of structural stuff, and hopefully some other things like FNIRS and eye tracking stuff later. Eye tracking. We got to get going on eye tracking. Okay. All right. So that's it. Thanks.